Hello everyone. In this video, we talk about binomial distribution. Let's take a look at an example. One part of a mathematics exam consists of 4 multiple choice questions. Each question has 5 choices, and only 1 out of the 5 choices is correct. Assume a student has no knowledge of the subject matter and randomly picks a choice for every question. The choice the student makes is independent of all other questions. What is the probability that the student gets exactly 2 questions correct? You can verify that this is a binomial experiment. What is the probability of success? Here in the question, each question has 5 choices and only 1 out of the 5 choices is correct. So the probability of success corresponds to the probability that the question is answered correctly is 0.2, 1 over 5. And the probability that the question is answered incorrectly is 0.8. What is the probability of getting exactly 2 out of 4 questions correct? There are altogether 6 ways to get exactly 2 questions correct out of 4. We can have question 1 and question 2 correct, and question 3 and question 4 incorrect. Or we can have question 1 and question 3 correct, and question 2 and question 4 are incorrect. So altogether, we can have 6 different cases or 6 different combinations. So we have 4C2, the number of ways to get exactly 2 correct out of 4 equals 6. How about the probability for each combination? For the first case, the probability is 0.2 times 0.2 times 0.8 times 0.8. The factor 0.2 corresponds to the question's answer correctly. In this case, which is question 1 and question 2. And the factor 0.8 corresponds to the question's answers incorrectly. Question 3 and question 4. Upon calculation, the probability of getting question 1 and question 2 correct, but question 3 and question 4 incorrect is 0.0256. In the second case, we have the expression 0.2 times 0.8 times 0.2 times 0.8. The probability is 0.0256. Similarly, we can get the expression for the remaining 4 cases. For each case, there are altogether 2 questions answered correctly and 2 questions answered incorrectly. So the factor 0.2 appears 2 times, and the factor 0.8 appears 2 times for all 6 cases. The expression for each case can be simplified to 0.2 squared times 0.8 squared. And therefore, the probability of getting exactly 2 out of 4 questions correct is 4C2 times 0.2 squared times 0.8 squared equals 0.1536. How about the probability of getting exactly 3 out of 4 correct? Then we have 4C3, the number of ways of getting exactly 3 out of 4 correct, and then the probability. We have the factor 0.2 appears 3 times, corresponds to the number of questions answered correctly, in this case 3. And then the factor 0.8 appears once, corresponds to the question answered incorrectly. So we have the probability expressed as 0.2 raised to the power 3 times 0.8 raised to the power 1. The probability of getting exactly 3 out of 4 correct is 0.0256. Let x be the number of questions answered correctly, and we have done the case, the probability of getting exactly 2 correct. We have p of x equals 2, and we get the expression. And we also completed the probability of getting exactly 3 correct. The expression is p of x equals 3, and we have the following expression. Can you see the similarity regarding the two expressions? The probability of getting exactly x correct, we have the expression p of x equals to x equals to ncx times p to the power x times 1 minus p raised to the power n minus x. If n denotes the total number of questions and x denotes the number of questions answered correctly, then the value of x can take on value 0, 1, up to n. And in fact, this is the expression for the binomial distribution. For the binomial distribution, n denotes the total number of trials. P is the probability of success, and x is the number of successes in n trials. We have the PMF of the binomial distribution. The probability of exactly getting x successes in n trials is given by this expression. We have shown it in the previous slide. NCX is the number of ways of getting exactly x successes out of n trials. And the factor p to the power x corresponds to the probability of getting x successes. The probability of success is denoted by p. We have x successes. So the probability of getting x successes is p to the power x. And then the remaining trials, the remaining n minus x trials are failure. So the probability of getting n minus x number of failure is 1 minus p raised to the power n minus x. Combining this all together in the expressions, we get the PMF for the binomial distributions of exactly getting x successes in n trials. For these binomial distributions, we use the notation, say the random variable x follows. B stands for binomial distribution, with parameter n corresponds to the number of trials, and p, the probability of success. Let's get back to our example. Let x be the number of questions answered correctly. And we have the PMF of x. P of x equals 0. That means all the questions are answered incorrect. The number of questions answered correctly is 0. So we have this expression, 4C0 times 0.2 raised to the power 0 times 0.8 raised to the power 4 equals 0.4096. And then we can have the probability of getting one question correct. P of x equals 2, P of x equals 3, and P of x equals 4. There are altogether 4 questions. So the value of x can only be 0, 1, 2, 3, and 4. And on the right-hand side, we have the graph of the PMF. This is the graph for the random variable x that follows a binomial distribution with n equals 4 and p equals 0.2. You can change the value of p to take a look at the different graph of the PMF. So here we have p equals 0.2. We can have p equals 0.25. In this case, these questions are giving you 4 choices, and only one is correct. Or we can have 3 choices for each question. In this case, p equals 0.33. Or we can have a true-false question. So p equals 0.5. This is the binomial distribution. And x can take on values 0, 1, up to n. So we can expect that the summation of p of x from x equals 0 to x equals n must be 1. So let's take a look at how we derive the 1 out of this binomial distribution. X can take on value 0, 1, 2, up to n. And if you investigate this expression is similar to the one given in the binomial theorem. The binomial theorem states that x plus y raised to the power n equals the summation of k equals 0 to k equals n of the expression nck times x to the power k times y to the power n minus k. If we replace the x in the binomial distribution by k, and then you can see the similarity. The x in the binomial theorem corresponds to the p in the binomial distribution, and the y in the binomial theorem corresponds to the expression 1 minus p. So this summation should sum up to x plus y raised to the power n. In our case, x equals p and y equals 1 minus p. So we get p plus 1 minus p raised to the power n. And then simplify the expression, we get 1. So we prove that the summation for x equals 0 to x equals n of the binomial distribution PMF equals 1. That's it for today's video. Thank you for watching. In the next video, we will compute binomial probabilities.